Hello everyone, I am Dr. Kiranmayi, Area Chair and Assistant Professor, Digital Transformation and Operations, Department of Management Studies, School of Business, Aditya University. In this present lecture, I am going to discuss how to formulate the problem as linear programming problem and how to solve the linear programming problem using graphical method. Let us consider a problem. There is a garment manufacturer who is producing two styles of shirts, style 1 and style 2, and using three different resources, cotton thread, decron and linen thread, and which are available limited in nature, and the objective is to the net contributions we are given, that is the profit upon each shirt we are given, and accordingly we have to formulate the problem as linear programming problem. And here the question is how many units of style 1 shirt and style 2 shirts are to be produced. These are the decision variables. Before formulating the problem as linear programming problem, we must understand whether all the prerequisites, all the requirements, conditions are fulfilled or not. Let us define the decision variables x1 and x2. Since the firm is producing two types of shirts, so the question in front of the manufacturer is how many units of style 1, how many units of style 2 shirts are to be produced. Let x1 number of style 1 shirts are to be produced, and let x2 number of style 2 shirts are to be produced. The decision variables we have defined, and then objective, the second step in formulation of the LPP. Step 1 is identifying the decision variables, step 2 is formulating the objective function. So, in this problem we are given that the contribution upon style 1 shirt is 19.50, the contribution of style 2 shirt is 15.90, and we have assumed that the firm is producing x1 and x2 number of both types of shirts respectively. Therefore, the contribution of style 1 shirt is 19.50 and it is producing x1 units of style 1. Therefore, the total contribution upon style 1 shirts is going to be 19.50 into x1. We have assumed that the firm is going to produce x2 number of style 2 shirts, and it is given in the problem that the contribution of style 2 shirt is 15.90. Therefore, the total contribution of style 2 shirt is going to be 5.90 into x2. To get the total profit, it is the linear, if we can sum up in the linear combination of the objective function, that is 19.50 x1 plus 15.90 x2 is going to be the objective function. Since we are considering it as profit, therefore the firm wants to maximize the profit. So, maximum Z is going to be this one. So, this is the objective function. And then next component of the LPP, the third step in linear programming problem is to formulate the constraints. So, we came to know in the problem we are given that the style 1 shirt needs 200 units of cotton, 300 units of decron, 300 grams of linen. Likewise, for style 2 also we are given the constraints and how many units of each thread is available, that also we are given. Therefore, here the conditions are upon the resources, that is the three types of thread there is condition which are available only in limited. Therefore, how much cotton thread is required? For style 1 200 grams. For style 2 how much cotton thread is required? 200 grams. And cotton thread is available only 24 kgs. 200 x1 plus 200 x2 less than or equal to 24,000. Since only 24 kgs of cotton thread is available, that is why we have to use less than or equal to. And likewise, we can formulate the constraints for other two resources also. And finally, non-negative constraints. So, we never produce negative units of the quantities, therefore, x1, x2 must be greater than or equal to 0. So, this is how we have to formulate the linear programming problem. And after formulating the linear programming problem, the next part is to solve the linear programming problem. So, the basic agenda of linear programming problem, this mathematical model, this optimization technique is to find the optimum solution. What is optimum solution? The best solution which either maximizes or minimizes the objective function. In this case, we have taken maximization. What is the best solution that maximizes our objective function? So, that optimum solution we have to find out. Here I am going to discuss graphical method. So, remember, using graphical method we can solve the LPP which involves only two decision variables. In that case only we can use this graphical method. Okay. So, in this problem we have two decision variables, so that we can make use of graphical method. And let me tell you how to solve this LPP using this graphical method. First, we have to identify the coordinates of each constraint to plot on the graph. First, consider the first constraint. So, in the given LPP, it is the first constraint, it is the second constraint, and it is the third constraint. After considering the constraints, identify the coordinates. First, put x1 is equal to 0. Replace x1 with 0 to find out the value of x2, and also to find out the value of x1, put x2 0. So, then you are going to obtain the values of x2 and x1. So, when x1 is 0, x2 value is this one. When x2 is 0, this is the value of x1. Okay. So, this is how we have to first find out coordinates of, in order to plot the inequality on the graph, this is how we have to find out the coordinates of the line inequality, right. Next, consider the next constraint. Put x1 0. If x1 0, this is going to be the value of x2. If x2 is 0, this is going to be the value of x1. Just you put in place of x1 0, that is 300 into 0 plus 200. Consider the inequality as the equation in order to find out the coordinates, right. So, x1 is equal to 0, 200, x2 is equal to 26. That gives x2 as 0.13. Likewise, we can also obtain the value for x1 by putting x2 0 in this equation. So, this is how first we have to find out the coordinates for each constraint. Consider each constraint as equation and obtain the values of the coordinates for the decision variables x1 and x2. So, this is how you can find the coordinates for third constraint also. And then after finding the coordinates for all the constraints, next consider the graph, and this is going to be x-axis is going to represent decision variable x1 and the y-axis is going to be denote the decision variable x2. So, the first constraint coordinates are 0.12 and 0.12. So, first constraint 0.12 lies somewhere here, 0.12 and 0.12. So, this is the first constraint. So, first consider the points, and this is 0.12 and this is 0.12, join both the points. This is the first constraint. And coming to the second one, it is 0.09, 0.13 on y-axis, 0.09. So, this is going to be 0.09 and what is the other one? 0.13, and this is the green line is the second constraint. So, join the points, and for third constraint it is 0.22 and first point 0.07, and this is going to be 0. The violet color line is going to be 0.07 and 0.22. So, this is how you have to plot all the constraints like this. And after plotting the constraints on the graph, now the next step is to identify the feasible region. So, what is this feasible region? Feasible region means the solution space, the solution region which satisfies all the constraints. So, let us start from origin. So, from origin to let us move to the right side like this. and this is the point where we have to take the turn, because if we move to the green line from the violet line, so we have only the left side region only satisfies. And remember, to identify the feasible region, always consider lower region for less than or equal to type of inequality. Consider upper region for greater than or equal to. Consider the region on the line for equal to type of constraint. Since here in this problem we have all are less than type inequalities, therefore we should consider the region below the line. So for this violet color, we have only this left side region. This region is not covered by this violet line. Therefore, here we have to take the turn. From here, this violet point, violet to red. Since we cannot move to the upper point because that is not comes under covered by the second constraint. So, this is how we have to find out the feasible region. Now, in this problem, the feasible region is, which is shown by the shaded part. Okay, and this is the feasible region. So, after identifying the feasible region, and next find out coordinates of all these points. So, this red one is origin, therefore it is going to be 0, 0, and this is on the x-axis, therefore y coordinate is going to be 0, and the x coordinate is, we know that 0.07, this is A and this is B. This is how. So, this B point, how you can find out this B point? So, B is this point. B is the point of intersection of this violet line and green line. So, solve those two equations, violet line that is second and third line, then you will obtain the coordinates of the point B. After finding out coordinates of all the points A, B, C, D. So, after finding out the points like this, so prepare the table and substitute these points in the objective function. Therefore, our objective is to, these are the different possible solutions. As in the beginning of this unit, we have understood various terminologies related to linear programming problem. One is feasible solution. There exist multiple feasible solutions which satisfies the conditions. Okay, but our objective is to find out the optimum solution. Optimum solution is that feasible solution which is the best one. Okay, therefore substitute these values in the objective function. Since at the origin the value of x1, x2 is 0, objective function value is 0. At point A, the value of objective function is 1.43. Substitute 0.07 in place of x1, substitute 0 in place of x2, you are going to obtain 1.43. So, likewise for all the extreme points of this feasible region, find out the values of the objective function at all the extreme points in this way. And after finding out the value of objective function at each extreme point, now look at the objective function. What is our objective? To maximize the objective function. Okay, maximizing the profit. Find out which feasible solution is maximizing the function. So, here which is maximizing? It is 1.43, it is 1.8, 1.98, and this is maximizing the solution. And this maximum value has occurred this point. This is maximum value. This extreme point is maximizing our objective function. Therefore, maximum value of objective function is 1.98. When this will be maximum? If the manufacturer produces 0.02 and 0.02 is the value of x1 and 0.1 is the value of x2. So, hence the optimal solution to the given LPP is 0.02 and 0.01 and the maximum value of Z is 1.98. So, this is how we can solve linear programming problem using graphical method. So, by the end of this lecture, we came to know how to formulate linear programming problem, and we also understood how to plot the inequalities on the graph and how to find out the coordinates in order to plot the lines on the graph, and how to find out the feasible region, and also what is the value of objective function at each extreme point. After that, we also understood that how to determine the optimum solution using this graphical method. Thank you.